Hey guys, Chelsea and I are going to go through the 2011 Free Response number 3, which is Thermo / Electrochemistry. So here's the question. So for letter A, they want us to calculate the standard enthalpy change for the reaction represented by the equation above, which is 2 moles of hydrogen gas plus 1 mole of oxygen gas, yielding 2 moles of H2O liquid. And they tell us that the molar enthalpy of formation for H2O liquid is negative 285.8 kilojoules per mole at 298 Kelvin. So we have the balanced equation, and the standard enthalpy change can be calculated by the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. So we do 2 times negative 285.8 minus 2 times 0 minus 1 times 0. And the reason the two enthalpies of formations for H2 and O2 are 0 is because the standard enthalpy of formation for an element is always 0. So we get negative 571.6 kilojoules per mole as our answer. In question B, we are to calculate the amount of heat in kilojoules that is released when 10.0 grams of hydrogen gas is burned in air. So we have 10.0 grams of hydrogen, and all we have to do basically is stoichiometry to find the moles of hydrogen in this amount of 10 grams of hydrogen gas. And then after we do that, we multiply the moles of hydrogen by 285.8 kilojoules because 1 mole of hydrogen yields this much energy. And we get 1.42 times 10 to the third kilojoules. And make sure you're careful for sig figs, as we had 3 sig figs here, so we have to end up with 3 sig figs here as well. In letter C, given that the molar enthalpy of vaporization for H2O liquid is 44.0 kilojoules per mole at 298 Kelvin, what is the standard enthalpy change for the reaction of 2 moles of hydrogen plus 1 mole of oxygen gas, yielding 2 moles of H2O gas? So we know that the delta H for the first equation is negative 571.6 as found in part A, and we're given that the heat of vaporization of H2O is 44 kilojoules per mole, And since 2 moles of H2O are made, multiply the second equation of vaporization by 2, and to make the coefficients 2, and then multiply the 44.0 by 2 as well, and add the two H's together to get negative 483.6 kilojoules. Here's the second part of the question. So in question D, we're supposed to write the equation for the overall cell reaction. So the equation with the greater reduction potential will be reduced, whereas the equation with the lesser potential will be oxidized, meaning that we'll need to flip the second equation because that has the lesser reduction potential. And then after we do that, we need to balance the number of the moles of electrons in both equations to equal each other. Then we cancel out the molecules that are in both the products and the reactant side, and then combine the two equations together to get 2H2 plus O2 yielding 2H2O. In question E, we're asked to calculate the standard potential for the cell at 298 Kelvin. So basically, to calculate the standard potential for the cell, we do the standard potential of the cathode minus standard potential of the anode. So the cathode is the thing that's being reduced, which is gaining the electrons. And the anode is the thing that's producing the electrons, or losing the electrons. So we do 0.4 minus negative 0.83 volts, and we get 1.23 volts. And a key thing to remember in doing standard potential questions is to not multiply the cell potentials by the coefficients that we multiplied the equations with to balance the number of electrons, because in standard potential you just simply subtract the two. We don't consider the coefficients that we multiply with. So in letter F, we are supposed to assume that 0.93 moles of hydrogen gas is consumed as the cell operates for 600 seconds. So in part A, they want us to calculate the number of moles of electrons that pass through the cell. And in part B, they want us to calculate the average current in amperes that passes through the cell. So for part A, we simply have to do stoichiometry. And so we know that there's 0.93 moles of hydrogen gas, and we know that from this equation right here, that 1 mole of hydrogen makes 2 moles of electrons. So we multiply 0.93 times 2 and get that there is 1.9 moles of electrons. For part 2 of this question, we are asked to calculate average current in amperes, and amperes is coulombs over seconds. So calculate coulombs from the moles of electrons that we found in the first part of this question. So 1 mole of electron is 96,500 coulombs, which is given in your formula sheet, so you don't need to worry about it for free response. And so we multiply 1.9 times 96,500 coulombs, and we get 1.8 times 10 to the 5th coulombs. And then, since we have the coulombs, we simply do 1.8 times 10 to the 5th over 600 seconds, because we are given that it ran for 600 seconds. And we get 3.0 times 10 to the 2nd amps. And again, remember to look for those sig figs, because those are a big part of this question. So letter G, some fuel cells use butane gas, CH4H10, rather than hydrogen gas. The overall reaction that occurs in a butane fuel cell is 2C4H10 gas plus 13O2 gas, yielding 8 CO2 gas plus 10 H2O liquid. What is one environmental advantage of using fuel cells that are based on hydrogen rather than on hydrocarbons, such as butane? So hydrogen fuel cells produce only water as a product, unlike fuel cells that use hydrocarbons, which release carbon dioxide. Carbon dioxide contributes to global warming, which is caused by the greenhouse effect. And we're all done. So good luck on your AP test. You'll be awesome, and thanks for watching the video.